thanks very much, everybody. So luckily, a lot of people have already given you a good overview of isotope systems. So lowly sedimentologists isn't going to have to get involved with trying to explain or understand what's going on there. I'm just going to take those tools and try and give you an overview of maybe some of the way we can apply some of the systems to a sedimentological problems. So how can we harness these tools we've learned about in sedimentological perspective? And it's all about using some of those geochemical signatures in detrital mineral phases. We could even touch on orthogenic mineral phases, so they're growing within the sediments themselves, to better understand something about sediment sources or intermediate grain history, so how they've gone from the source to their or to the sink that you're analysing them in, to have a better, more complete understanding of not just sedimentary processes, but we'll show how that can relate to deeper time earth processes as well. And I guess thought kind of quite late that potentially Pete had intended me to talk about provenance in a broader term, that maybe not just sediments, that provenance of different various materials like archaeological, maybe some stone tools or different kind of traffic materials or illicit goods, but some of these same tools can be used in the same way. So why should I care? I imagine at this stage you were all hoping to get to tea, and now you're being subjected to sedimentology. So why do we care about these? So paleogeographic reconstruction is one of the earliest kind of tools or applications of these tools of understanding how different continents were arranged, understanding how orogenic systems were connected and where the sediments were being spilled from. Stratigraphic correlation, and sometimes this can be for economic purposes as well. So you might be able to get a distinctive kind of detrital signature within a particular unit and be able to say something about maybe reservoir connectivity in hydrocarbon systems. More economic perspective, place of mineral systems, particularly heavy mineral sands in Western Australia, it's quite an important one, but equally for understanding where other resistant mineral phases, diamond, gold, that sort of thing, how they are being concentrated. But obviously for maybe more an academic perspective, we use it for improved resolution of the geological record. So due to the lovely processes of weathering and erosion, that tends to destroy a lot of the primary crystalline metamorphic igneous rocks that most of you heathens are interested in. But those minerals, those sort of signatures of the processes they represented, can get preserved in those detrital minerals and stored in the rock record. So it's an excellent archive of Earth history. So for understanding things like sediment generation, routing, basin formation, broader scale geodynamics, it's important for this. And like I say, more resolved geological record where things have been lost. So particularly looking at the early Earth. So this is some of the earliest approaches to just understanding sediment provenance, looking at the basic composition of sediments, quartz, feldspar, and lithics, and being able to relate the fact that distinctive environments typically yield distinctive compositions in sediments. But obviously we've moved a long way from these early kind of plots, and we're now using these new analytical tools to much more at a grain scale level understand where sediments have come from. So, basic geological map of Western Australia. How are we going to possibly, what can we measure in an individual grain to understand where a grain of sediment has come from? And this is where the geochemical tools come in. We need something that's going to be sufficiently distinctive to be useful in defining what kind of geological province it's come from. So we need some sort of signature of the different array of tools we've used before that you're not going to find across the whole of Western Australia, that everything has the exact same signature in the crystalline rocks, because then it's not going to be at all distinctive enough for us to be able to use. That signal has to be stable enough that it doesn't get modified during sedimentary processes. So it doesn't get reset, it still links back to the source. And you also need it in a mineral, housed within a mineral that's going to be stable at Earth surface processes, Earth surface pressures and temperatures as well. Because if you are storing an isotopic signal in the mineral, it's going to get destroyed very, very rapidly during sedimentary processes, it's going to be useless to you in the sedimentary record. So obviously some of the things we've looked at already is the fundamentals of using uranium-lead geochronology to get some sort of age of crystallization. Maybe you'll look at different mineral phases, again, uranium-lead system to look at maybe a cooling pathway. Maybe later on we're going to hear from Martin and hear about uranium, thorium, helium dating to get that very, very low temperature signal. But some sort of age of crystallization, cooling, something that is unique to a certain region, that you know this region experienced this sort of orogenic event, tectonomagmatic processes of a certain age that you can say, ah yes, grains with that signature have come from there. Or you can look at something a little bit different and look maybe at a snapshot of an evolving isotopic reservoir, maybe looking at the lead isotopes of feldspar, and when they were extracted, they will store that information, and similar to the hafnium isotopes, they're changing so slowly that we can reconstruct what they were at the time that they were extracted. And we'll touch on a few of these with some examples through this talk. So one of the main ones that people have been using for a long, long time is everyone's favorite mineral, apparently, zircon. We'll see how the mineral cup goes this year, whether zircon survives. But I'm not going to go through this again. We're looking at the fundamentals of being able to retain age information in zircon crystals and use that as a diagnostic kind of fingerprint of the source it's come from. So you can get quite complex grain histories preserved through the use of these cathodoluminescence images. We can start recognizing not just maybe that it's come from an igneous rock with a certain age, but you might be able to say, okay, well, it's come from an igneous rock of a certain age that was influenced by metamorphic processes at this later age. We can be much more precise at being able to constrain what source region had those particular characteristics to then be able to say that that grain has come from that region. So you can obviously characterize the grains in situ to understand which kind of portion of this very simplified, smaller map you are looking at grains being derived from. And as people said, that we'll touch back on again, the zircon, extremely robust, and it also incorporates other elements that are useful for us in terms of diagnosing that grain, in terms of hafnium, oxygen isotopes, trace elements that give a more precise geochemical fingerprint. Something that we will be looking at quite a lot if you are looking at detrital zircon provenance papers is actually comparing the one-age population to another. So we were looking at Terra-Rossberg diagrams and weather plots, but when you're not looking at a single age population and you're looking at more of a detrital population, it could be taking grains that span everything from 100 million years ago to maybe 3 billion years ago. And that's sort of an array of grains. You like to see that sort of the relationship of where those grains are with respect to each other and where the densities of those grains are, which maybe is lost somewhat when on top of Terra-Rossberg, the grains are plotting on top of each other. So you look at these sort of different visualization approaches, and there's various different ones with different kind of drawbacks to them. Things like the kernel density estimator, which looks at the ages of your grains and plots them out according to their density along that space. So it gives a little Gaussian curve for each grain, and it gives the uncertainty on that Gaussian is being basically dictated by how concentrated the grains are or the ages are in that space. You can do a similar thing with a probability density plot, but this time you're using the Gaussian uncertainties being produced by the actual uncertainty on the age analysis. The difference between these two plots has the grain ages exactly the same, except you can see that some precision on some of the analyses is very tight, and that basically gives it an extreme peakedness, which could maybe draw your eye into thinking that that peak is more significant and that age is better represented in that sample. So you just need to be aware of what you're looking at with the way you're plotting it to determine which age is the most significant. Because ultimately what we're trying to do here is to say, okay, well, we have a lot of grains in this age interval, and so we're going to be looking for a source region that was producing a lot of zircon grains of that age interval. Ultimately, is the overall aim of this. And you can also do histograms, which is the, everybody knows. Starting out, this is what people do, which is comparing these curves in a very basic way. And obviously, we need to get a bit more robust about this and actually look at statistical testing of how similar these different complex age populations can be to one another. So this is how the individual grains would plot out as ages. This is how they then produce these probability plots. And we can then convert them into these cumulative distribution curves at the top there. And then we can start applying different techniques. Ones that we particularly prefer is this KS distance, Cooper distance, and it looks at the maximum distance you see on these cumulative distribution plots. And that will enable you to statistically say this population is more similar to that population. So it can give you a bit more robustness to your argument of saying that maybe these two sedimentary populations and this complex array of ages in these sedimentary populations are more or less dissimilar. And there's a number of different kind of online tools that basically do this for you. So it makes life very easy. Ultimately, what we're trying to do is something like this. We have different crystalline basement source regions with distinctive ages. So blue and green here on the left in the map. And they produce age spectra, something like that, graphically shown. The blue one is distinct from the green one. If we mix those together and we derive sediment from both of those source regions into this sediment area here in red, you're going to ultimately end up with some sort of a spectra that's a combination of those two. Now in this case, it's very simplistic, and it's taken them both in equal proportions and overlaid them together to produce something like that. Now the realities in natural systems are that there's going to be some sort of biases. There's going to be maybe greater catchment area in one area. Maybe there's going to be greater fertility of zircon in another area, which is going to skew this ultimate kind of pattern we see. So things like the tectonics of those different regions, the actual composition and chemistry of those different regions. Maybe one is more felsic than the other source region, and that's going to influence ultimately the zircon produced into the sediments. And obviously there's things like facies controls as well, the sedimentary processes impacting how the sediments get fractionated. But ultimately what you're then trying to produce is some sort of reconstruction of the transport pathways to the sediment profile you're looking at. And of course, we can add layers of complexity. It's not just a simple matter of taking sediment or eroding material in mountains and taking it straight to the sea. It goes into the basin and it's preserved forevermore for you to analyze. There's a number of different things we need to think about. There's intermediate sedimentary basins or intermediate storage it gets trapped into. Those basins can then get uplifted in the subsequent orogenic system and get re-eroded and retransported multiple times, and that all impacts the overall sediments that you ultimately end up with. So here's a little test to see if anyone's still awake and how simple this process is. So we've got three different samples here. We've got sample A, sample B, and sample C. And we've got very simplistic ages 1, 2, 3, and 4. So what ages are represented in sample A? Yana?
3 and 4.
Oh, anyone differ in their opinion? Is everyone happy about it? If you got that one, you're going to get them all. Very good, Yana. Top marks. Yeah, so you're going to see this reward. You're going to see some contribution of the mountain system, maybe some intermediate sedimentary systems age signature into A. In B, we're mixing 1, 2, and 4, and in C, you're going to have some sort of mixture of all of them together, where we have this mixing on the shelf, tidal currents, etc., etc. So comparing those different sediment reservoirs, you might be able to get a handle on detangling that system to understand where these different age signatures are coming from. And I'll touch on some other techniques we can use that we've developed to try and understand sediment mixing a little bit more complexly. Okay, so this is a little example of how they might look in reality, some of these different age signatures for different sediments from around Western Australia, and particularly just color highlighted the different regions we were interested in. So all of these age spectra are different sedimentary kind of basins, and the vertical color bars you'll often see in these sorts of plots are the classic ages we associate with crystalline sources that they might be derived from. So you can see that the Yilgarn Craton classic ages is explaining a lot of the older stuff. We have this Albany Fraser Wilkes and maybe Musgrave Province explaining lots of the Proterozoic material. We've got some Pinjarra origin, we've got some kind of Kunga, and we have some Eastern Australia material there as well. So here we were looking at the similarity of these different sedimentary basins and trying to understand the sources that they came from. So relatively simplistic kind of ideas. Can anyone tell me some of the characteristic ages we see for the Albany Fraser origin? Mike, did you PhD on there? Can't remember. Yeah, okay, let's go with 3900. Can anyone tell me the characteristic ages, maybe the Musgraves? Similar?
0.3.
There we go, so the same thing. So what the hell do we do where the ages aren't unique? So there's the biggest problem that you've all probably thought of. Zircons, you give it the date, but there could be multiple rocks it could have come from. Okay, so the issues arise there with a simplistic kind of approach that you're not going to get a unique answer necessarily. So this is when we bring in the fun and games. You might be wondering, who the hell is this guy up here? No, that's not why I'm going with this Guess Who game. What we're doing with geology is something similar. We're going to start layering on our different techniques, our different geochemical tools. So instead of asking about facial characteristics in this game, like does this person have glasses? Does this person have red hair? You're going to start asking questions of what age did this grain crystallize at? What age did this experience cooling at? What age was this extracted from the mantle? And by doing that, sort of layering in this geochronology, thermochronology, isotopic signature, we're going to convert this game into a guessware. And we're going to be able to start knocking down the different potential source regions and start coming up with a more and more refined understanding of where these grains have come from, and then link this sink sediment back to its original source. So starting to demonstrate how this can be useful, we could look at double dating. And in this case, these images on the left are taken when we consider the uranium lead age of crystallization and the uranium thorium helium age of a cooling. And you can start to see, okay, well, the grains would have crystallized at depth. They then would have been slowly brought to the surface through denudation of the land surface. And so there's going to be typically a lag time you'd expect between those two ages. Now, when those ages are perfectly coincident, then you expect that to be volcanics, basically. It's both crystallizing and essentially being erupted to the surface, cooling at the same time. So you can identify that as a quite unique population. And you can use that where, say, if we look at the uranium lead ages, previously these B and C populations, these source regions, B and C, were essentially indistinguishable in uranium lead age space. But when you actually start looking at the uranium thorium helium ages of them, they were denuded and uplifted at different times. And now you can differentiate B and C, but A and B are undifferentiatable. So by bringing the two of them together, we can start teasing apart all of these 5 unique sources, whereas otherwise, if you only used one of those systems previously, you wouldn't have been able to detangle. So there's just a schematic example. This is an example from real sediments from underneath the nullable plain, where we identified volcanic signature in most of the grains we were looking at. But equally, we identified older grain signatures that were matching of broader burial systems within the region. So you can start differentiating the grain histories according to intermediate basin storage and then re-exposure versus volcanic production and incorporation into the sediment. And obviously identifying a volcanic component gives us some more information in that it could be helping to constrain the depositional age of the sediment, where otherwise you might not have that, you might just have a max depositional age. Let's go a step further. Let's go to triple dating. You can understand what I'm doing here now is just layering on more information. And in this case, we're looking at uranium-lead age, we're looking at uranium, thorium, helium age, and we're also looking at the model age from lutetium and hafnium. And by incorporating the three of those different measures, again, we were able to constrain where sediment from Southwest Australia had come from, and suggesting basically it's coming from Antarctica underneath the ice, and you can start actually being able to say things about hidden bedrock that is sealed beneath that ice as well. So obviously with these examples I'm showing you, they are age information, but you're not necessarily restricted to only using age information. So just kind of taking a step beyond some of those simplistic ideas of what people had previously done with matching a sediment to a source, or trying to match a sediment to a source, is looking at what can we do beyond looking at isotopes as provenance indicators. So we can look at global compilations now. Obviously, people have been working on detrital zircon geochronology for decades, and consequently, hundreds of thousands of millions of analyses have been undertaken around the world, building these global compilations, and we can start teasing them apart into these different regions to help understand maybe patterns on, like Mike was touching on, are there changes in production, preservation of those signatures? Can we start saying something about supercontinental cycles, or just relationships of these different cratonic blocks? Like I said before, if we can recognize orthogenic minerals or contemporaneous volcanics, maybe we can get absolute ages. And I'm going to touch on two different new techniques we've developed recently in terms of looking at the age population demographics. So what I mean by that is, where are the ages distributed and how are they distributed, to understand something about maybe the basin setting. So what sort of tectonic setting do these sediments accumulate in? And how much sediment mixing had undergone. And we're also going to touch on using the radiation damage of those crystals to track something about the degree of sediment transport and recycling. So it's getting into that deeper, closer to that original, true natural variability of these systems. So here is a little plot from South America. We're obviously on the western seaboard. We have subduction going on. We've got a volcanic arc. We have got then a transect across to the passive margin on the east coast. We've got various different geological units indicated here. They've undertaken a whole host of different sediment samples, analyses of detrital zircon signatures in modern sediment. And we looked at the age spectra. And anyone that's looked at these age spectra before, you'll notice that anything from an active kind of volcanic system tends to have a single age mode, and that age mode is very close to the depositional age of the sediment. And anyone that's looked at a passive margin tends to see them being quite polymodal, and it's not crazy imaginative to think, okay, well maybe we can start using those signatures to say whether you're in a passive margin setting or convergent setting. So Haywood in 2012 came up with a model trying to work on this that required depositional age information. And what we were trying to do with this study is basically say, well, we don't actually need depositional age information. We can do this based purely on the spectra alone, and this will allow us to then look at systems in the Proterozoic where we don't have depositional age information well constrained, or where that depositional age information is dependent on the zircons themselves, to then basically make it a bit more useful. So we looked at the heterogeneity, so how polymodal these samples are, and we used this modified chi-squared test to basically capture that and quantify how polymodal they are. And we looked at the age gap between the 10th percentile and the 50th percentile to come up with this new system that would classify your samples for you. So if you see any red samples, that's saying it's an active convergent margin. If you see darker and darker blue, that's saying it's going towards more of this passive margin. And you can see it quite nicely captures the active side running through and becoming progressively more and more mixed, and capturing that heterogeneity of the basin geology as we head towards the east. Some of you are probably spotting some of the blue things here and saying, what the heck's going on with that? Yeah, I can tell you were thinking it. I can definitely tell. Does anyone know why they're blue? Why is it just that we did a poor metric? Could be. I would argue that it's because basically it's a localized signature. So where that sample's been taken in that river system, it's capturing there are Paleozoic different kind of sediments caught up in this origin, and it's recycling those zircons. If we follow that river system down, and it's had a chance to capture more of the volcanic systems sediments, then it becomes red at the bottom of that river system. So if you take a very, very local sample, it's showing you the importance of realizing where your sample is coming from and what it represents. If you take a local sample, it could be just telling you something about the very, very local conditions. But if you give it time in a broader system to equilibrate with its setting, then it should tell you the real kind of story. So this is a new tool that we've presented for understanding tectonic settings, and just one of the examples we used in the paper. Another bit of work this time by Max, who's not here, one of the PhD students working with us, is looking at the radiation damage that accumulates within zircons as a result of that uranium-lead decay. That radiation damage accumulates according to things that you measure normally during this provenance work anyway. You measure the age, you measure the uranium and thorium composition, ppm in the grains, and you can do a calculation of how much radiation damage you would expect within that grain. Those radiation damaged crystals should be more susceptible to being broken up and destroyed during transport. So if we then measure the radiation damage in the detrital population, and we also then compare that to what's in the crystalline source region, we should see this is what it should be in the source region, this is what we have, and it's shifted significantly. We've only now got the low radiation damage versions of the full population we'd expect in the crystalline source region. All the high radiation damage crystals that are in the source region have been destroyed during transport. We can quantify that by comparing one to the other. A value of 1 suggests that basically you're taking sediment that's just come straight from that source region. And we have an example of that kind of sediment sitting on top of the granite it's come from, and it has a value of 1. And as we look at these different systems, we saw sediment that's only a little bit removed from the crystalline basement, and it's shifted slightly. That material is thought to have been recycled into this, and you can see it's lower again. This material has been thought to be recycled into this, and you see it's shifted lower again. So constantly as those grains are being recycled, you're seeing a lowering of the source normalized alpha dose as those grains are being destroyed. So it's indicating something to do with the degree of sediment reworking and recycling. So it's quantifying those processes to some degree that otherwise previously were lost going from that. We know it's come from this ultimate crystalline source. We know it's in the sediment now, but how did it get there? And there's a number of different kind of tools we can start layering on. That's a lot on uranium lead and what we can do with it in zircon. But there's a range of different mineral phases out there with different characterized kind of isotopic systems that you might be interested in, and the temperature that they all relate to. So when you're doing this, I guess you need to think about what kind of temperature closure you're thinking of, what the composition of the source region may yield for you to actually analyze. And trying to solve these non-unique solutions by those integrated approaches is pretty critical, because there's a whole host of biases with any individual single system. One of the things that's quite neat with this O'Sullivan paper is demonstrating that you have zircon is blind to these orogenic systems that don't produce much, which aren't very magmatic. Okay, so sometimes if you base yourself purely on these zircon provenance work, you're going to be blind to some fairly large-scale magmatic, very large orogenic systems which have low magnetism associated with it, and you might need to look at other mineral phases to try and recognize them. Feldspars, Jan has done an excellent job, so I won't go too heavily on this. So this time, again, like we've talked about, we're taking a detrital feldspar grain. What I will add is that one of the cool things about feldspars is that they are more labile than zircon. So they will get destroyed more during the kind of weathering processes, and because it's less hardness, it will get destroyed more during the physical transportation. So typically, you don't see it getting recycled multiple times. So some people will argue that feldspar is a good one to start comparing with zircon to try and understand the sedimentary system of first cycle versus multi-cycle. Feldspars are also much more common in plastic rocks, so they're framework versus accessory mineral. So does that mean that because it's maybe up to tens of % of the rock, that it's more representative of the overall sediment you're looking at? So whatever you see in the feldspar, where it's telling you the sediments come from, it's actually more representative of the entire bulk rock because it represents more of that sedimentary rock. So that's one thought. Another person might say, but zircon's resistant and so is quartz. So maybe the fact that zircon's going to get recycled, quartz is probably going to get recycled. So maybe zircon is actually telling you a more representative signature. I'll leave that with you to ponder which one is more accurate on that one. But it does point towards the complexity we're dealing with in these systems. So essentially we have these, the evolution curve of the lead isotopes. We can extract feldspars from different points along that. Feldspar shouldn't incorporate much uranium, but as Yana said, it can sometimes. And so it should hold on to that ability to fingerprint the lead isotope signature of the source. This is what we were doing with Greenland. And one of the things it pointed out was, despite the zircon, we coupled it with zircon, like Yana was saying, and despite the zircon having a very, very pronounced signature of this Proterozoic source, the feldspars were saying it was more coming from this Paleozoic clevenide source, suggesting significant amounts of reworking of the sediment, of the zircon signature. And I think I'll leave it there. We've got to keep in mind your biases. Make sure you're doing appropriate sampling for what you're trying to do. Appropriate sample processing, that's where a lot of biases kicks in. Good characterization of the grain so you know what you're doing. Consider whether your source has been sufficiently characterized. So obviously we have a wealth of geochemical characterization of crystalline basement in Western Australia, but that's not always necessarily the case. You might not have characterized it all. You need to think about what your data actually represents. Is it first cycle, recycling? Is it uplift, metamorphism, crystallization? Whether the source region is felsic, mafic, this is all going to have different kind of interpretations. And then you just arm wave as much as you want, because it's likely that you haven't characterized, and no one knows everything. There's always room in sedimentary systems for a bit of arm waving. So I will leave it there. Thank you very much.